later. But before that, just jump into the sequence. So I say I'm going to talk a little bit about THIN-WALL-2. And I talk about the background of those two, THIN-WALL and THIN-WALL-2. And I will touch a little bit, not much, about the finite strip. What really the background, the theory background behind that. It's not just a software, but of course there's a whole theory behind that based on a finite strip method. So it's totally big area, and probably you need another course to do that. Just focus on the theory. But in this context, or in this lecture, I just quickly introduce to you. And if you're really interested, just email to me. I will send to you all the document or all the paper that you interested, and then you can look it further. And I will go through step by step. Just walk you through all the, like a manual, how to do it, how to use it. And at the end, I will play around with the program here directly, so we can interact and then we can play around with that. There's a lot of things, fun things to do in the program, and particularly not just about designing direct strength method. You can use for your teaching or your normal design routine as well. It's very useful one. Particularly, you calculate the material property, and then you can do it by without doing by hand calculation. Okay, that's the beauty of THIN-WALL-2. Everyone hear me clearly at the back? All good? Just raise your hand if you couldn't hear me or you want to make anything clear or whatever. Just let me know, okay? Now, background of THIN-WALL-2. So THIN-WALL-2 is the baby, I think, what it calls baby. So Professor Craig Hancock is the one who actually wrote this THIN-WALL program. So at that time, in '93, he wrote THIN-WALL program based on finite strip method, and used Fortran program for coding. So years ago. And the first one, the one that we introduced to the audience is the THIN-WALL. The previous edition now it doesn't exist anymore because we have THIN-WALL-2. But you used to have the THIN-WALL in our website before my time, before I started my PhD. So at that time, Professor Hancock wrote the engine, the XZ5, all the theory behind it. And Dr. John Papagilis is the software manager who wrote the interface for the program using Visual Basic. So just on Dr. John Papagilis, he's a PhD student of Professor Nicholas Traher. That's I keep telling you about the flexure torsional buckling work. So he's one of his students, and he's worked in our school as the software manager. So he looked after all the software and all the licensing or the technical support. So even THIN-WALL-2, we are the one who developed that. But if you have any question on the THIN-WALL-2, you should contact John. Right. So with the THIN-WALL-2, now we talk about THIN-WALL, the other one. So that is the cross-section analysis for open section, and also can analyze the closed section as well. So THIN-WALL is normally open section, right? Can be C, Z, or hash, or whatever shape that you wish. But it can be closed. You can close the loop, like circular, rectangulars, or any type of closed section. And the THIN-WALL-2 use the BFIN engine. What we call engine is the file that is run analysis. So at that time, THIN-WALL just analyze analyze the compression and bending only. And then after that, THIN-WALL-2 start when I started my PhD. So it's my baby, or my student baby, and Greg, Professor Hancock. So we extend the THIN-WALL. Yeah. So it means that THIN-WALL is the base. We step on and extend it, not just we develop from the beginning. However, that THIN-WALL-2 has a little bit more, I think much more now, function that you can use. That is combined two sub-programs. They're all written by Professor Hancock. Just give you a bit of information about Professor Hancock. He is a distinguished professor in cold-form steel structure. However, when he did his bachelor degree, he got 2 degrees. One is computer science, and one is structural engineering. So that's why he's very good coder. So he knows how to code the program. So that's why, without surprise, he's very good at that. So he wrote the THIN-WALL-2. THIN-WALL-2 is a big program, and there's two engines on that. Depending on what you use. BFIN-7 is just for normal stress, and BFIN-10 is for localized loading. I'm going to talk about it later. But that is when you remember when you copy your file that I sent to you instruction, there's 3 files, right? One is the exe file to run the program, and there's 2 engine files in here. So make sure that you have those 3 files in your directory. Okay. So then what next is my PhD student, Dr. Van Vinh Nguyen now, start to use different graphic user interface. So we developed the interface by using MATLAB. We're not using Visual Basic anymore. So it gives it a lot of option and friendly and nice interface. So I'm going to show it you later. So that's why we developed that, we finished, and we complete that, and we put on our website. So there's 2 versions, and one version is what you got, is for education purposes, and that is free. And then one version is for commercial purpose. So normally the companies in worldwide, and particularly in Australia, when they produce or they design for cold form steel, normally they buy a license for that. So that is 2 separate. I will tell you what difference between two versions, 2 editions. So what news in THIN-WALL-2 is this one. So we including shear, and we include localized loading, and then you can design for that. So those ones are new and will be different with the program CUFSM. You aware of that? Aware of that program, right? So that program is very similar to THIN-WALL, the previous one. But now THIN-WALL-2, we're having a little bit more than what they did. Is we can design for shear, and we can design for localized loading. So this is comparison between those 3 versions. This is the one previously I told you, and this one is the THIN-WALL-1 that you got, 1.1 and 1.12. So they are slightly different, but not much different. You can do a lot of work loading in your free one. The only limited is the number of nodes. We limited for educational version is 100 nodes. So if you make a very complicated section, you need 200, for example, then you need a commercial edition or version. Other than that, you can do it. And other differently is when you solve the localized loading, the free version is just limited to simply supported at 2N. But if you want other type of boundary condition, fixed end, pin end, or whatever combination of that, so you need to use the commercial one. But that's just for localized loading. For compression, bending, and shear, you can do it exactly the same in the free version. So another thing is in the 1.2, we got one function just to do everything for you, which means that you can design based on direct strength method. So you don't have to do all the what we're gonna do. Put in the DSM equation or check lambda whatever. You just put that into here, click the button, and then work it out for you. It gives you straight away PN or MN capacity. So this is for the commercial one, the company, if they want to save time, so they do it. But for you, if you don't want it, that's fine. You can run that, follow all the DSM methodology, and you can do it. Okay, so it's just nothing really fancy here. It just make it available here for you. That's it. And the other function that different is with the commercial one, which you can click the export and then we'll export for you the whole report. And this is very important for company when they want to put a bid or design package something, they can export the report. And also for this one, it allows you to actually draw the cross section on AutoCAD and it just import that to THIN-WALL-2 and run that. You don't need to work it out by hand or Excel or whatever. Okay, so that is just something new, or now some differences between those two programs. But in general, you can use that without any problem. Okay, you can solve all that for the general purposes. So now I will cover a little bit about history of finance strip method, which is behind the THIN-WALL-2 program. So have you been familiar with finance strip? Or I'm sure that you're familiar with finite element, right? Everyone probably design. ETABS, so American software. Okay. You have any Indian software development? Okay, so you use mostly. Okay, so ETABS, is it? Yeah. So it's for high-rise. This is the American one. Okay. SAP. Yeah.
What's that? STAT.
STAT. Oh, STAT. Yeah. Okay. So there's SAP as well. Yep. Yep. So in Australia, we have equivalent MicroStrand and Strand 7. So we got our own program, but just all based on finite element analysis. So finite strip is not popular as finite element, but it's very suitable. I think somehow it's suitable for. It's better for cold form steel because you can cut to the strip along the length of member and run analysis. So it's very simple. So that's why it fit with cold form steel. So I think I talked to you a little bit that before, but now give you an overview about finite strip method. So it developed by Professor Y.K. Chung in 68, long time ago. Professor Y.K. Chung was from Hong Kong. And he moved to Australia and he was a professor at University of Adelaide, one of the, so the capital city of South Australia. So one of the top of 8 best university in Australia. So Adelaide is one of them. So he's the one. And Professor Greg Hancock got a book, I told you that story. So he inspired by that book. And they were good friends. So, and later on, Professor Chung came back to Hong Kong and was a professor in Hong Kong before he passed away 2 years ago. And then Professor Hancock normally spent time sabbatical or teaching in Hong Kong. So they got a good relation. So that is the history of that. And then further developed by Professor Whitchett. So he's one of the famous Professor Whitchett. So just give you a bit of background. I like to talk about other things that I know to share with you rather than just the name of the paper, what they did, but a bit of things behind that is interesting. So Professor Wittrick is the first, I think. So he's from UK, and he's the first student, the first PhD graduate. So he got the first PhD in our university. So we founded in 1850, 175 years ago, but faculty engineering later on. But then we offered a PhD degree, and he's the first one who got a PhD degree. And he was in faculty of mechanical engineering, I think, in Sydney Uni for a while before he heading back to Birmingham, I think, in UK until he passed away in UK. So he's not civil engineering, he's the aerospace professor. So you remember with THIN-WALL, in aerospace industry, they're probably better than us, right? They deal with a lot of complicated THIN-WALL structure of aircrafts and all that, with all the running of of the frame of the aircraft, with all the holes, and everything is more complicated than in structure. So then Professor Greg Hancock started to use all the theory behind them, and then develop for cold form steel. So that is the history. So Professor Hancock started to write one of the very famous paper from him. And if you have a chance and interested in research, you should download that. So this is the first paper that he gave definition of distortional buckling. So he got a signature curve that we learned yesterday and then probably today. And this paper is the first time in the world that people know about distortional buckling. Okay, so just something that you are interested, and then you can have a look. And this signature curve that we talked yesterday is based on that work from back into 1978. Right, and then later on, Sammy Lowe and Craig Hancock. Sammy is the one of PhD student, very smart, back into to 1986 and 1989. And Sammy now is a very high ranking official in Ministry of Transportation or something in Hong Kong. So he back in Hong Kong and work. He's not an academic, but he's still working in bridging department or something. So we still keep in touch with those students of Professor Hancock. So just on a side, Professor Hancock has not many students of him. So he got about 17 PhD students until he retired. So I'm lucky I was the last one. And normally we check each other where they are, and then sometimes we get together, we have chat. If we are academics, so normally in conference we talk and meet together. Okay, so Sammy. And then later on, very good work by Conan Hancock. So this is all the paper that you should read that. So this is Professor Yang Kon. So he's from Korea and one of the very distinguished professor now in Hong Kong. I forgot the name of the university, but in somewhere in the middle of Korea. And he's now working on different area, but still structures. If you look up on the internet. And then I'm jumping to play with shear. So I'm using start to dig on that, but using different type of finite strip. So what I did in 2009-12, I start to look at shear problem, but using splice finite strip method. So those one on the top here, Professor Hancock used semi-analytical finite strip, the psi function. But later on, when I jump in, so I'm looking at different ways to do it. I'm using splice function just to use for finite strip method. So with this one, That publication is the first one in the world. We're lucky that to publish, to introduce the shear buckling of the whole section. So you imagine like in hot rolled steel or even in cold form steel, before that, normally with shear, we just look at the web panel, isn't it? When you design any I section or C section or whatever, to check for shear, normally just split the panel, the web panel only, because shear is carried by web mainly. However, from this work, so we found that you need to take into account the flange and lip, the whole section carry the shear as well, not just only of the web panel. So that's why that paper came up, and then it gave like about 15% or 20% more than we just treat as a single web member. So that's why from this publication that we integrate into the standard now. So if we use DSM in shear, and we're using the shear buckling coefficient or shear buckling load for the whole section. So based on our work in here, back into 13 years, 15 years, or maybe more than that, I think. So pretty long, but it's good to start with. And then later on, Craig and myself, we try to think of different ways to do instead of splice finite strip. So we start to play a bit of theory using complex mathematics method. It's a little bit complicated math, but we can solve for shear. And you remember, shear is not simple. Bending is the buckling shape is simple face, but shear is 45 degrees. Somehow it is more complicated we thought. So we have to use complex mathematics to solve that one. Or the other way we can use is we use multiple term theory. So I've explained to you before, we're not only using one term. We have to using multiple terms to pick up the boundary condition. Then that's why we can solve for shear. So those publications, if you're interested, you can look at that, and then we see how we develop the finite strip with different techniques. So we can include the shear in that. All right, just give you a bit of the highlights, and later on, then we look at the localized loading for the theory part, not the design part. So my first PhD is Dr. Nguyen. That's the one that the key person behind THIN-WALL-2. He developed all the interface by MATLAB. So we developed the theory behind that. Using finite strip, semi-analytical finite strip, but we do it for general boundary condition. So normally you have simply supported is the easiest way, right? But now you can do everything. You can do it with different boundary condition, with a fixed end, a pin end, or even mix of them. You can do analysis of those in every condition now. So those papers give you a big idea about how we develop in terms of the theory. All right, so and then what happened in here, we all integrate all the theory that behind the THIN-WALL-2. So in the THIN-WALL-2, you can use every function of that, and each function actually behind is the theory that we develop here. It's just not simple like a function, it's all based on the theory that we developed for many years in Australia. Right, so for those who would like to know a little bit, maybe one slide on finite strip. So finite element is we divided member in an element, right? You got 4 nodes, or depend on whatever element you choose, and you have. For finite strip is we cut the section into multiple strips. Okay, so and then the thickness is virtual. There's no thickness in here. So the cross section is the line. Okay. So that's very relevant to THIN-WALL-2. It's for THIN-WALL structure, cold-form structure, because cold-form and THIN-WALL, the thickness compared with the dimension of the whole section is very small. So we can actually consider as a line. Right, so this is a strip that we cut it out. And now I can show you this is all the finite strip theory. So this is nodal line 1 and nodal line 2. And this is all the degree of freedom. And this is all the displacement function. Okay, so that we use in finite strip. And what else? Then we develop the theory behind that, where you have the eigenvalue routine. And K here is the stiffness metric, and G is stability metric. So that all built and code into the THIN-WALL-2, and then you run it. Okay. So to do that, you need page by coding, but that's done by Professor Hancock. So and then we compile in the exe file that you have, and you run it. Okay. If you want to understand a little bit more that one, please look up in our paper that I just sent you, and then we give you a big an overview, a background, and you're gonna go to the reference, and you can look at some history and literature review as well. Okay. Right. So this is not our purpose today. Just give you an overview. Then now I'm going to the program. So when you double click on the XC5, then that window will come up. Right? So this is the interface of the THIN-WALL-2, and in the help you can click to authors, and then they're showing you three authors. That is Professor Hancock, and then Dr. Van is one of my first PhD student. He developed that MATLAB, and then myself at that time. Okay. Then before that, if you have any technical question, then you need to have support. Okay, you need to contact John. So you click on help about THIN-WALL-2, and click on and support, and you got all the detail of Dr. John Papagilis. So just send him an email, and he will reply to you if you have any problem with the program. You can send to me, but hopefully I can help, but he's the best person to help. Right. Okay. So all the email address, phone number, and everything in here. Right. And then now this is the flowchart of THIN-WALL-2 program, how it works. So first you start with THIN-WALL-2, and then we need to define the input. We need to tell THIN-WALL-2 what we want to do. You know, create section, create the material, or whatever, and then assign the boundary condition, and tell them what you want to do in compression, shear, or whatever, and then you're gonna do it. And then you run the and then you assign the restraint. Restraint is mean that the boundary condition you can do, and then on your left hand side is for uniform loading. So and then on your right hand side is localized loading. So they are slightly, they are different, right? So uniform loading is when you're looking at how to design the columns and the beam or shear. So they're all uniform loading along the member, right? So that is how you follow on the left here. On your right hand side is when you would like to design for localized loading. So it means it's something, as I explained to you, the beam sitting and the support, and then under the load here, there's highly concentrated load. It might cause the web crippling problem or localized loading on your member. So the load acting at very small area, and then it causes the web crippling. Then it's called localized loading in here. Then this one, you follow that to design. Okay, so that's two functions that you do. And at the end, once you put all the inputs in the program, and you tell THIN-WALL-2 that what you want to analyze, and then you run buckling analysis. And then from buckling analysis, it's gonna give you some outcomes. Is buckling load, buckling shape, give you a signature curve, right? So give you all the everything that you want, material properties, and then stress distribution as well, and then you can visualize, you can play around, you can understand, you can cut the section, or you can zoom or rotate or whatever. You can look at that. Okay, so how you got that at the end in here. Okay, so now, then you get the main window. Have you everyone try successfully? Huh? You get to here, right? Okay. So what I do now, I go step by step into what you should do or you want to do, and then later on, I will jump in to play one example, and we play around with that. Okay. So first is THIN-WALL-2 version 1.1 here, showing you which version you got now. So of course, definitely you got the 1.1, and I got my 1.2 with me in here, and I show you that later on. But slightly, they are very similar. If it's not available, it will be hidden like this one. Okay, it's there, but if 1.1 you don't have that function, so it's hidden, or it's gray here. So this is the menu bar, and this is the toolbars. And this is the context bar. So you can easily click on the button on the bar, and then you can get the function straight away. And those window is a result tree. So you got all the result on the left in here, showing you everything. And this one is a result bar. So you can choose different failure mode, or you want to look at stress or whatever. It's going to be here, showing you here. Right. So now we're starting a job. So you click on 5 and create a new job. So make sure that you then need to save to a directory that you want, all right? Other than C, you save into your hard disk or anywhere else, and then and every file later it will be in that directory. You can click a new one when you start a new one, but while you already create a job, and you just stop there and go somewhere, and you want to come back, and then you want to keep doing that, and you start to open instead of new. So you open that, you can have the file, then you can open it again. So with save one, then you go to here, give them a name or the project that you want, and then save that. And then first thing is you choose a unit. So of course in here, I think in India you use SI unit, right? But in UK or in particularly in US, they're using slightly a lot different, not slightly. So you need to select power or inch or whatever, and you can do it in here. So first we choose unit, format unit, or two ways to do it. One is you click on that, or second is you click directly on the bar, just the shortcut, so you don't have to go to that one. So there's two options, two alternatives that you want. Right, so then you can choose here millimeter, newtons, and then you can click OK. So just click whatever you like to use, and then OK. Yep. And next step, then you need to tell THIN-WALL-2 about what material you use. So you can click on define and material, click on that, and add. So normally when you click on by default, the steel material is available. Normally we use steel, and then we can add that one in. So when you click add, you add in, and then normally it gives you here all the property of steel. But you can actually vary. You can change in here if you want. So for example, in shear modules, sometimes you use 80,000, sometimes you use 76,500, whatever, and you can change in here. or sometimes you use 210,000 megapascal in US, so you can change that. And in the library here, we have a couple of standard material. So you can put aluminum, or you can put bronze or zinc or whatever. We already integrated in the library. But not just limited to that. You can put the user, click on that, and you can create your own material. You can come up with whatever, later timber or composite material, whatever the material you want to assign. To click on that, you can put the input in here. You can assign. Okay. And then you need to tell THIN-WALL-2 about element type. So element type is, I'll explain to you a little bit later. So you can do, you click on element type, you can see 2 in here. So remember, I told you before, with finite strip, the thickness is not true. Yeah, it's the virtual thickness. So the cross section is the line. So we need to tell them the virtual thickness. So that is the element thickness in here. So in here we tell them it's 2, and 2 is the 2 millimeter element thickness, and it will go around of cross section. Okay.
Why is this TG?
TG is for shear, and this is for bending. But normally we put 2 of them. It's the same. Yep. Yep. In cold form steel, normally you come from one coil. It has the same thickness, right? However, in here, not in here. You can actually. So here you create the first element is 2 millimeter, and later on you can create another element is 6 millimeter, and then you assign the strip. Okay, so the flange, you put element 2. So it's going to be 6 millimeter all the way for the flange. But the weft, you put element 1 is 2 millimeter. So in order to do that, you can assign several or multiple thickness within your cross section. But other than that, if the cold form, you have only one thickness, so that's fine. All right, good question. Yes? Yes, that's what I explained. For welding?
Welding sections.
Yeah, so for I section, right? So I section is, you can use the web and the flange with different thickness. I show you the little bit of arrow in the finite strip, because the finite strip, what I'm talking about is finite strip treat as a line, and the thickness is the virtual one. So for example, you got this one, the strip here. So this is, for example, 2 millimeter, okay? But for the weft, it starts from the center line here, because it's a line. So it's gonna be like from here to here. All right, so the strip here, like this one. So it means that in here, somehow you got that area is overlapped, but this area is missing. But in general, the total area is roughly the same, roughly accurate, but it's not 100% as the geometry of that one. But as I said before, you can assign this one 2 millimeter, you can assign this one 1 millimeter by selecting different element, or even different material as well. In a composite structure, sometimes you use top flange is steel, and the web here you use in aluminum, for example. You can do it. Okay. Sorry?
How the 2 different material or 2 different thicknesses to become a single section?
So you have to tie them together by the same node in here. I show you how to tie them into the node. So but they're sharing the node 1, 2, 3, and this one 4, 5, and then this 6. So this strip has to be connected by node 3 and 6 to connect those together. Okay, so I show you how to do it later on, but this part of the finite strip. So it's actually the strip along the node, and the member thickness is the virtual one. Yes?
I got confused with the TE and TG. Is the thickness of bending what you mean is flat and thickness of shear what you mean is bend. Is it right?
You mean welding?
It is normal section.
Normal eye section, yeah.
TE and TG.
No, that is for analysis, for shear and so just don't worry about that. Just keep them exactly the same. That is just complicated when you run the shear and not shear buckling. But I'll give you a bit of a theory behind that later on when you run for the theory. But at the moment, you just keep those the same thickness when you run the general. Okay. So in here, you can see that we can choose the element with different thickness, but make sure that you choose thickness for shear and thickness for bending. But at the moment, you just put it exactly the same. Right? And then here you can choose steel or whatever you assigned before, your own one, you know, and then you can click on here, it will drop, and then you choose on that. And then next, you go to section. Okay, and then you got all what you want, material, element, then you can create your section. So as again, there's two ways to do it. Right? You can click on that or you can click the button on the toolbars. It's up to you, whatever you feel comfortable. This is the bar, you can click on that and you can create that. So when you click on, the one pop-up window will go up. And in here, the THIN-WALL program has some common section that normally used in the practice in the industrial application. You see section Z, L, and in here we're also using I and T. So it's span section, you can do it. CHS, RHS, and then a lot of the other one that you want. Okay. So you can click on that. For example, C section. And you can get it. Other than that, as I mentioned before, you can create your own section. So by clicking on General Section, you add it, and you can copy from Excel, from spreadsheet, all the coordinates of the mode that you want, copy and export into THIN-WALL-2. You read it, and then it will draw it for you. Okay. So that is how we can do it in general section. I find this function is very interesting because not always you're using the normal section. So normally we solve that one for a company where they want to play around with optimums of their section. They play around, they put stiffener, they want to put a little bit stronger or put a little bit smaller, or vary size or whatever. So they're using that one a lot. In their development of their section. THIN-WALL-1 has the general.
Doesn't have this copy paste option. If we need to input the coordinates, then we have to type it and input, not copy paste.
I remember you click on that and you click on the button and you just click paste. Okay, I'll show you later. You highlight in Excel all the coordinate that you want, and right click, copy, and then you go to here, click on paste.
The paste option is not.
Previous version it is not that.
Is it? I'll try later. I mean, I can't remember. Maybe not. But let me check it again. Okay, thanks. All right. So when you click on C section, it pop up in here. The C section, and then there is in here a couple of things. C section in here, you can choose unlip section or lip section, and also we put the Super C, that is the patent from Australia. So you can actually use that, you know, without creating your own one. You can choose that, and of course you can play around with more complex section. You know, like this one, got one stiffener. You got one small triangle stiffener or 2 of them. All right, so that is the available section that you can use, which are available in the library. So you don't need to create. Just click on that. I will ask you all the dimension that you want. Just input it. All right. So other than that, you remember you see here, because it's a coral, then it allows you to input the radius as well. Okay. So in here, normally in Australia, the internal radius of cold-form steel is 5 millimeter, but depend on the thickness, right? So if you have got a thicker one, 6 millimeter, maybe the internal radius may be bigger, you can input that. 6 or 8 or whatever, you can change that in here. And remember, carefully look at the figure in here, because the figure here showing you maybe the overall dimension, okay? This is overall dimension, but in final shape later on the coordinate, they will back calculate the center line dimension. So whatever, you need to look at the figure showing you. So this it look like it's overall, and then you just input the overall section, not the center line. All right, and then you click on that, I will show you this table. All right, so this is all coordinates of the node. And this is all the strip definition. So the strip mean that is the strip between 2 nodes. Okay, so strip number 1 is between node number 1 and 2. Okay, so this one what you have in here. And in here is the element type. So you can click on that, you can change. So what I'm saying before, you know, from element 15 to element 26 is the, in the web you want to make it thinner, you just change element here to the thinner one if you like. Okay, and that give you a different thickness. And this one is what I show you when you export to Excel. It means that you can got that connect and you can export out and you use for someone else or something else. So it gives you a connect of that. This element type that I talk about, you can change and then you insert that. Define general section, that's what I talked to you about. So you copy, you use that, you highlight. Remember, you need to have a node as well, the node sequence, 1 to 13 or something. And this is a coordinate X and Y. And you just highlight, just from 1, not this one, okay? Just highlight all that, right click, and then you see, click on paste in here. You can do it. I think you can do it in 1.1 version, but I'm not sure. I'll check it, okay? Click paste, and then apply. So as I said before, you can change in here. The reason why, when you do it, they just connect the node automatically. So it means that a strip file will be connected by 5, 6 or something. But with the plain section, yeah, it's not always like this one. You need to pay a little bit of attention on that. We can changing the strip in here just to make it. So I show you the example of how it works later, what I mean later. And then you assign halfway length. You remember in signature curve, we got a 40 halfway length, and then by default, THIN-WALL-2 will give you the stress and then the halfway length, and they plot for you the whole signature curve. But sometimes you need to know exactly where you want. What I'm saying here is, for example, you got a signature curve. Okay, so this one is roughly 200 something. This one is 800. This one sometimes, this is the halfway length of the whole member we learned from yesterday, right? So this can be, now it's every, like every even number. 7,000 and 8,000 or something. But if you look at, I want to design a column 7.5, how am I going to do it? So you need to 7.5 halfway length to input. You actually add, you can add that one. So it means that in here, you want a 7.5 millimeter, and you can add that before you run. So you add that, you run it, the thing will give you exactly where you want. And of course in here as well, sometimes the minimum is not really exactly. So what I'm saying like here is 200 and 220, for example. But when you want to refine that area, maybe you want to look at 210, maybe that is come to the minimum, not 200 and 220. Then you can actually add that one in to make it exactly where you want. So that is where you can add in here, and you can add halfway length in here. Right. So what I'm saying here, that's what I'm saying. You got a 40 halfway length. It's running from 30 millimeter, 45, 50, going all the way along to 10,000. And you can actually add somewhere in the middle, like I say in here, to get your design halfway length that you want. Okay. So by default, we got 40, but you can add and then modify if you want. Now, uniform stress. So as I explained to you before, now we need to apply the load. So to apply the load, you got the first is uniform stress, and then you click on stress resultant. So now you tell THIN-WALL-2 whether you want to run for beam, column, bending, compression, or shear. And remember, this is the uniform stress. So that's what happened in our member, nothing to do with the end, right? So you don't worry about barrier condition, it's just normal stress, uniform stress. So that's what you do. And then you click on uniform stress and stress resultant, or you click another option, and you come up to here. That is the stress resultant that you want to put in. So axial load, that you can put a bending or the compression or tension. And in here bending, you got a bending about X, bending about Y. And you can put shear in that, shear in X and Y. And other than that, you can put bi moment, warping torque, and St. Vernon torque. Have everyone been familiar with bi moment? It's a little bit complicated, right? Particularly for THIN-WALL. So it's very interesting if you really in THIN-WALL or cold form seal, and you should learn more about bi moment and warping, everything in here. Okay. But this is, if you really dig in that area, then you can input that to, but in general, you can put in here. Right, so if you click on MX is the minus, it's up and down, just minus or plus. So you can see the rotation arrow here. So this is, when you apply that, it means the top flange will in compression. So that is bending. And then you can, now you start run analysis. So in analysis, you can see when you click on that, you have section analysis. It means that when you run it, it will give you all the material, mechanical property. And then you click on that, and then the program will run, and they give you here. Okay? They will give you centroid. They give you shear center or everything. You don't need to go to the appendix and make an idealized section for square angle, and then you calculate. And now it's give to you everything. And then on your left hand side, they give you, see, area, IX, IY, the centroid, shear center, moment of area, and everything. Torsion constant, J, I, W is warping torsion, and everything that you want for your analysis. Okay. So I think that function is good for not just for buckling analysis, but you can use for your design. You know, you can play around with any type of section, and you can get roughly or the mechanical property that you want. And now buckling. That is where we get the signature curve. So you click analysis, or in the other, you can click on that. And then you click on your lab in here, you got a uniform stress. And then you click on stress analysis and buckling analysis. And then you run it. And that will show you the result. Now with the result, you go that and you can click on the buckling result, click on signature curve. Then it gives you the buckling signature curve. All right, and then in here, you can see with THIN-WALL-2, we make a little bit different. Is on your vertical axis here, we put the load factor. It means that, you remember when you put on 1000 minus or something Newton, right, millimeter, yeah. So this is the initial bending that you apply. Everyone aware of the eigenvalue, right? So you put initial one, but you run it, you got a load factor. So it's actually the eigenvalue. So it gives you load factor. So now local buckling is about 1000 times. So is it, sorry, yes, so it's 1000 something. It means that our buckling moment at local buckling is the 1000 that the initial one that you want, multiple with that. So that is the MOL. That's one you have, okay? So that's how you get it. And you can click on that, it will run from left to right and it will show you exactly where you want. And will pass through the minimum and you can click on here, they will give you that minimum, all right, already. So the minimum here is about 120, but you look in here, maybe 105 or 01 is lower, and then you can input into what happened at the beginning again and run it. And they will give you slightly different. That's it, where you can play around with that. Now with the version 1.2 is for commercial one, you can click on design and you can click on bending and that's it. It gives you all the equation, all the thing that you want. So at the end of the day, what you see that? They calculate for you MBL, that's what we learned, MBD, MBE, MB and everything, and then they got 5 factor I check for you. So it means that when you got the THIN-WALL program here, and you just click one button or 1 or 2 buttons, and so you got all the answer here. Easy, right? So it's showing you a direction curve. This is the local buckling curve, and this is distortional buckling curve. So interesting here, you can see local buckling lower. You know why? Because of interaction between the global and global. Okay, so that's why. But then if you can hear, interesting here as well, it gives you the lateral restraint as well. So you can see if you put a lateral restraint in the middle, you see it's buckle, then it will reduce your LO, EZ, or EX, or whatever we learned from the effective width, remember? So that it will affect your buckling load. And that will give you a different answer to play around with that, okay? So that's very interesting. And then again, I explained before that we can create the report. That is important for company where they want to put everything in a document. So we can export that, and then you can export into the text file or Word file, and then you attach to your document. And you can click all the information that you don't want or you want, and you can do it. Okay, so this is roughly about the step. I'm sure that you get lost somewhere because you can always look at that. Look back is the manual. However, after break, I think we can play with that for real one. We can have a bit of hands-on. Okay. Other than that, just show. I put that one many times, but just showing you. This is our grad hall in the University of Sydney, where this is the ceremony for accreditation from us. As you can see, the building is very similar to the building that you watch in Harry Potter. Yeah, so so all the design, all the stained glass and all that, Sydney Uni copy a lot, very similar to Oxford University in UK. Even our gown for graduation, everything came from Oxford. So it just give you a bit of background about where it looked like and how it looked like and where we got influence from. So good to share. Hopefully we welcome you. Some of you maybe to Sydney. Let me know. Yes. Can you talk louder, please?
Material property.
Material yield stress. Okay, that's a good question. I think you can. In the design, you remember with buckling, there's nothing to do with yield stress. It's just in design. So in design here, that's where you put the yield stress. It's 450. Okay, you can put anything that you want because it's related to design. So in here, it's showing you where you input the yield stress. Yeah. With buckling, you need this stability problem. It's not a material problem. Yes. Yep.
So while we are dividing it as strips in the curve, so how are you going to incorporate that shear variation? Is it going to be same parabolic variation or is it linear? Some of the papers I have read it as.
You mean that shear signature curve?
Distribution in the cross section.
Yes. Okay. So shear stress distribution is fundamental shear distribution, right? So when you got a channel section and you put the shear load up here and the shear flow will like this one. And this is parabolic. Okay, so that is how the shear flow will run along this. Okay, so that is stress distribution, yeah?
When you take a strip.
Strip?
When you take a strip.
Yes, that is really good observation. So we have to make a bit of trick. So we actually have to make it like step. So we consider each strip is the constant one. So we step on that and vary, okay.
Then a strip and constant variation.
Yep, but it's English. And that will give you an idea about what different here are. In shear analysis in here, remember analysis, structure analysis, this is shear flow. So when you add them up together, it's not in equilibrium, isn't it? If it needs to be in equilibrium, what is going to be? It's going to be balanced with what? Moment gradient. All right, so that's why we're not going to do this one with the moment gradient. But the beauty of finite strip is we can isolate it. We forget about it. We just input the shear flow, forget about the normal stress caused by the moment gradient. So we a little bit fake this one, not fake, we can work around to isolate shear without the influence of the bending. Okay, so that's why in shear in here you can get the minimum point. But with finite element analysis, we're using abacus or whatever, you can't get it because it's in equilibrium. So it is a product of the moment gradient, so you can't separate that. So the only way that you can separate is using finite strip. It's good. That's good to share with you something behind that, some secret that we don't tell people. But we've done shear for many years. We went to any conference, everyone talk about us as one of the pioneers in shear problem. But we have to be honest, it's still tricky problem. We spent like 14, 15, for myself, nearly 20 years, but still not understanding 100%. It's still tricky sometimes. It's not really clear cut as the compression or bending, because it's so you can separate them, but with shear is your relationship between the shear and bending and compression and all the interaction.
Longitudinal variations.
How long?
Longitudinal.
Yep.
Cross-sectionally, your thickness is constant. So when you consider around the length, how that variation will be considered?
That is tricky one. It's hard, yeah. Because at the moment, finite strip, you see, we consider as the uniform stress along the strip. Yeah. I think the other way you can do is ply finite strip or something. Yeah. But with ply, we can make it better, so closer to finite element. But the more we do that, the more complicated we put in finite strip, and we lose the simplicity of that. So what is that? It's not worth it. Then we use finite element straight away, easy, yeah, straightforward, give you an accurate answer. So either you like very simple, and you can see, click a button, done, and straight. Otherwise, if you want a more complicated, and using finite element. I think it's very, very suitable for design. Yep, good question. Thanks. Hey, anything else? You want to make an announcement or something?
Just, you know that we're supposed to break for tea.
Yeah, sure. All right, so we can have more questions while we have tea, and then we come back, and then we can have fun with the THIN-WALL-2 program. On this one, this is where we want. Let's have a look what the cross section that we want. So D is 200, B is 75, and L1 is 16.5. That's very typical Australian dimension of C section. Okay, so we're happy with the number of strips, and we could.
It becomes 1.5. Element type to be 3. Then only the thickness becomes 1.5.
So now we
the earlier diagram box.
the early one
The previous diagram. Back.
here,
Add section.
C section.
Say, yeah.
Oh, you put in here, right?
Element.
Yeah. So what happened in here?
Yeah. I will take 3. No.
Yeah, I see lip section, right? So you did here. So it's two here.
Element type to be
Yeah.
That left side element type will be selected as 3.
3. Then it becomes 1.5. Already we have taken third element.
Okay, see, yeah. So the reason I want to show you is we can change this later. Okay, right. So that's good. You can do that one here.
3.
But yeah, 3. That's it. So really good. All right. So the reason why I want to show you, because we actually come here and change in here. So each element is not just all. So the reason then now we're gonna look at how many elements we want to be 1, 2, 3, and you can actually play in it. So that's why my purpose is want to show you that. But any good point. So we can start here because we need 1.5. But as always, you can change in here. You can see that that strip 10. So so 10 here somehow. You see where? So it's gonna be 2, right? So it's thicker. So if I apply, you can see that it's thicker. Okay. Okay. So that's how you can change the thickness of the element. But we can do a 3 here. Apply. All right. So at the moment, automatically, the corner of the cross section, we we assign 4 strips on that. But of course, you can do more if you want, or you can take it less. But I think 4 is, should be good enough to our problem. So this is a section, and then we click OK. So that's cross section that we have. And then on the right hand side here, you can click on that cross section. You can turn on, this is node allocation, this is strip allocation, yeah, and this is the restraint. So later on we play about where we're going to put restraint or not. So you don't want to show it's too much information, you just click here, you hide the node number, or you can show the node number, you hide the strip number. So that is flexible for you to do it. Okay. And what next? We need to apply uniform stress, because we look at the bending problem, right? So we go at stress. And first is, remember we need to choose halfway. And remember our problem is 7.5 millimeter. And you're looking here, you got 7, 8. You don't have 7.5, you just click there, add. And you're going down to the end, and you add 7,500. You apply, and it jumps to here. You can see that? A new halfway length has been added, 7,500. That's what we want to look at. And click OK. And then we go to assign restraint, not restraint, because we don't do the localized loading. Then we keep going to stress resultant. This is where you apply the actual action on that. So in here we want to do bending moment. So for example, we put 1 Newton meter, or let's just say 1,000, just make it easier. It's 1 kilonewton millimeter. We click OK, you can see here. So if we put positive, it means that your bend is upside down. So normally you want the other way around, right? So you go back to that, you go to uniform stress, you just put minus on here. And you got that. All right, so that is, so you got section, you got elements, you got loading, that's it. Now what you do? Next is you go to analysis. So first you click section.
Support conditions.
No. We don't need support condition here because we're dealing with uniform stress. So we all the way. Support is where you do a localized loading. That you need a support. In here it doesn't matter. It can go from 41 halfway length. And we can see, but that's a good question. Then how we do that one when we design? You remember last time? So that is different when we need the length or support. Okay. So now what next? We run section analysis. Okay. So on your left hand side is showing you some number. Now can you check the number? Is that correct with what we did? By manually?
So you have given flange is 80.
Is that plan 80? Let me have a look on section. So we can go all the way, you can go back and define. Modify. Where should section data is it? Oh, 80. Is that 75? Okay. What else?
16.5. Lip is 16.5.
Oh, 16.5. So I remember we did it.
And the element type is 3.
3. Oh, okay.
Then only it will do.
That's it, right? Apply. Again, apply. and then OK. Okay. That's it. That's what really the section that we look like. We run again. Section analysis. All right, now we can compare. Exactly the same. Yeah, so you see that 412.76, slightly off, but then remember, you see that Y is slightly off, right? Because it's finite strip. So they treat one strip as a rectangular. It's not exactly like the accurate, but slightly one. So we accept that. So exactly the same. IX is the very much the same, isn't it? Very accurate. See how good now? So what else do we compare? Now look at the location of C center. What is that? 52 something.
2.56 here.
Yeah, so what you do, you plus this one and plus the one. You got 50 something, isn't it? Exactly the same. But you can check in here. You can turn that one on. And you can turn this here. C and S is centroid and shear center. Okay? And this one you can put up one is the principal axis. So this one is singly symmetric, it's easy, but it's a principal one. But when you deal with the Z section, then it's a little bit different, right? The principal is a little bit inclined with the web, so that is different problem. But this problem you can show the principal axis in here. All right. So this is Z, all the section modulus. Have you checked the full one? ZX. Check the Z full section modulus. Did we do it? Yeah. Yep, on page 39. Right? Yeah, so you can back calculate the ZXF, I think. Okay, you got it? Yeah, so that is the section modulus of the full section. Okay, that's good. So we can click on. What else you interested? So it saved you a lot of time, right? You look at how you calculate IX is a little bit painful of breaking down to all elements and working out the tables. But this one you give a click, that's it. What else I want to do? So I want to look at the analysis, and I want to look at uniform stress. Okay, so it's finished. So I can see here, that's the result on your right. You can click on pre-buckling and buckling, okay? So the reason why we have pre-buckling analysis and buckling analysis because it's all for localized loading. For uniform loading, you don't have to worry about that because the stress is distributed constantly along the member. It doesn't matter. So you just put straight away the stress in the member and run buckling analysis. However, with localized buckling, we don't know exactly the stress distribution. So that's why we need to run the pre-buckling analysis to get the pre-stress. To get the stress distribution and to get the deformation before buckling. And then we run buckling analysis, then you got all the eigenvalue and buckling load. So that's two problems separately. But that is just for localized loading, but not for uniform loading, okay? So this in here on your right hand side showing you the result. So you can click on here, signature curve. Right, so this is showing you the signature curve. We learned alright, right? So this is halfway length. This is all the detail that you want. You actually can click the 3D and it's showing you one halfway. You see? That one halfway. Right. and it's close to 500 here, it means that you see distortional buckling. So the lip is actually open, a little bit up, so it's 1. So remember, this is halfway. If I have 5 meters or something long, it's just, another halfway, and just go up and down for distortional buckling. That's how it works, halfway length. Okay, so you can actually click on 2D, it's a cross section in the middle. You can see that, this is up, right. So this is right in the middle here. So it's actually the distortional buckling. And this is where you choose 500 halfway. You can actually start from small one, 40. It's really local buckling. See, the junction line here is straight. It just buckle in the flange or a little bit in the web here. That's local buckling. And it's going down to 7. You see that? You can change here to. And then gradually you go to 80, 90. But the THIN-WALL-2 showing you here already the minimum point. So for the local buckling, halfway length is about 120. It's about that. Sorry. $120. Sorry, give me 1 minute. Just a moment. Okay. You got it now? 120 is the local buckling. And then it's going up. And it's going up to 140, for example, it's going up. But it's still local buckling. Okay? And then you can see it's still going up, still local buckling. Going up, still local buckling. So this junction, pay attention on that junction line. Still straight. Just buckle here, up and down, in and out. Just very local buckling. And go up to 200, local buckling, 270. Then you can see now it's going down. So from here to here, then change the mode, right? Change from local buckling to distortional buckling. And you can see slightly that one moving up in the middle. So it starts to open. So that's distortion buckling, and it's going down. And it's here, you see that they picking up the minimum point is 600. Okay? So that is really, so you can scale it up if you want. So you see that? You see it clearer. You can zoom it up like 3 times. So exactly, you see the failure mode of distortional buckling. And you keep going when it's longer. For example, 2 meters. Now, you can start to going down. And then, you see what is that? Flexure torsional buckling, going down. Okay? So, now, what interesting here? What you see, why, when it's buckled? Yes. So right in the middle, it buckles sideways and twists. Right? Get it? Yes. And what else you think? What interesting in here when it's flexure torsional buckling? Look at the cross section. Yep. What happened to the cross section? There's no distortion. It's just 100% there. It just twists and turn. You see that? C-section, exactly the same with this one. It's just moving out and twist. So it means that this is just depending on the length, right? The section, if you put a little bit of stiffener, it doesn't matter, it doesn't help, right? So that's its member capacity, okay? Right, so what really we're interested is 7.5, right? That's our halfway length and see what's going on. So we're going down, going to that. So that is the beam. You remember 7.5? The if we don't have the okay, you see that? If it's a bit hard to see, but it's here. And we come back to the value later. I want to show you the failure mode first in here. So we're going to 7.5. That's a long one, okay? You actually click here and you can rotate and you can see. Okay, you can see that, the beam. What's happened to the beam? Oh, okay. See that? Okay, yep. So we can increase the scale and we can rotate that. Yep, you see that? The beam actually buckles sideways and twist in flexor torsional buckling. Okay, so this is the MO node that we got. So look at your node. What is that we calculate from standard? So what we calculate is, yeah, let me have a look, okay. Yep, in here, 7.6, right? 7. Oh, no, that is the M node. Okay, so we can't actually, okay. Now, can you give me a hand? Can you do my favor? So you remember M node is a buckling load, right? You have CB factor. You remember? You got CB. And CB take into account that. But this one not. This is uniform loading. Okay? Get it?
1.2.
Yeah. What is that? CB? Really?
1.2.
Yeah, so and you can divide it and you get the pure moment. I want M node without CB. Can you help to calculate and then we can compare with this one? Everyone know about what I'm talking about? So our M node in page 38. M node is CB times with A times with R node, 0 node, and square with FO, FY and FOZ, okay?
Remove 7.612.
Yep.
Even in slide 39, 7.612 MO.
Yep, but that is for,
MO.
yeah, but with CB.
Yeah.
So what I want is here, you take the CB out, okay? You just take this one.
CP is how much?
298.
Yeah. So you just divide it. 5.8, yeah? We see what is that. Okay. Right. Another thing that we need to learn about behavior. All right. Look at equation M node. You get FOY. You're under the square root. We got FOY and FOZ. So this one represent FOY, and this one represent FOZ. So that's why the equation has two that one. So this is the failure mode here is flexural and torsional buckling. Okay, so that's how. It doesn't have FOX. because FOX is the bending down. Doesn't matter. It doesn't buckle this way. It buckles sideways and twist. So that's why you got FOY and FOZ in your buckling of the beam. Okay, so that is very important. Very important for you understand the behavior. So let's come back to here. Go into 7.5. And my number now showing that buckling load is 1.3. So time with 10, right? We put 10, right?
1,000.
Yep, so about 13 something. Doesn't make sense.
1,000.
1,000, right? So you time with here, so you got one, and you divide it by 1,000 is kilonewton, and then 1,000 is 2 meter. So you have to divide with 1 and then 60. You got it? You got this one. You time with 1,000 is you got Newton millimeter, and you divide it by 1,000, you got kilonewton millimeter, and divided another 1,000, you got kilonewton meter. 1.3, yeah? Is that?
Here it will be 1.3.
Yeah, and your calculation of
Please 5.8.
something not right? Oh, yeah, because, yeah, I know why. Because in here, you put pricing in the middle. That's good one. So then what we do next, we look at 3.4, divided by 7.5 divided by 2. So what is that? 3. Really good, really good. So we need to add the, so we have to unlock it, okay? Sorry. We unlock it so we can modify. So we actually define. So what we do, we have to change our, to add another halfway length, right? So what you want is 3.75.
3,750.
Oh, 7.5 divided by 2.
3.75 millimeters it should be.
3.75 meters. Here you have to it is millimeters.
3750.
3750. Okay. Apply.
No sir, 3.5.
Where's that?
Delete.
Oh yeah, okay. That's fine. That's good for you practice. You can actually delete it and add another one. Doesn't matter. All right. So 3750. Apply. Done. Okay. So and then we run it again. All right. So we see what it shows us. Analysis, buckling analysis. Okay, and then we go to the result. And we look at 3750. So the load factor is about 4.9. So what you calculate is 5 point something, is it?
5.86.
Okay, so roughly similar. So this is the accurate one, but the equation that you work is based on the energy method. Okay, and when energy the energy method, so it's slightly there's a approximation in that. So we have a slightly different. But this is how it works. On that one, we can compare. Okay. Yeah, because in the standard, the equation that we calculate is already based on the idealized section. Everything is a little bit here and there, and we ended up, but slightly different, but it's acceptable on that one. All right. So we're coming back to our problem. So this is very important. That is the signature curve. Okay? Got. Now, if we want to design for that, we click. We haven't learned DSM, right? So we leave that one for tomorrow when we design that. So another example I want to play is the column one that we did yesterday. Okay, and we see how we go. So we go and define again. So we unlock that. We go and we define again the section. Now I want to do beam, so I add another section. Oh, sorry, I want to do columns. So leave columns. And what is the dimension? So depth is okay, depth is 100, and B is 75, and lift is 16.5. Okay, and then the thickness is the 3 is 1.5. Anyone agree? Okay, is that right? The one that we learned, right? Apply and done. And that is the second that we do. We choose that, and this is the column. Okay, that's good. Now what we do, we run we put the stress distribution here. We don't put bending. We don't want bending, but we want compression. So we put minus 10. Let's say minus 1,000. Okay, we put that one in. You see, we compress it, and then we do exactly the same. We run analysis. No, we do the section analysis first. Okay, so can you compare now? Okay, so you got I is 3.155 something. Is that correct or not? Area is slightly different, right? But 400, 405, that's fine. And J is 304, 300, roughly same. Everyone happy? Yep.
It's not 63, but what is this? 61.
Which one is different?
It's not. Here's it.
Shear center? Shear center is the, yes. Yeah, let me have a look. So shear center X node is 65, and here 65, correct? That's great. What else? All right, so I think we got what we want, and then we run buckling analysis. All right, so now we look at the signature curve. So this is local buckling, and all that what we want. Similarly, we can move to the lower failure mode, and you can click on 3D. So it's compression. You can see the top and the bottom planes will be the same. It's buckle in local buckling. And then if we go up to a little bit longer halfway length, you see that it start to shift from local buckling to distortional buckling. And if we keep going to 350, no, other than that, The maximum is 500, 400 now. It's really distortional buckling. Okay, so it's open now. So it can be open or in, doesn't matter, right? It's changing the halfway. You can have that. And then it's keep going to 500 and 2000, okay? Seconded here. Then it's still, cross section is still open. It means that it's still in sectional capacity, right? It's not member yet. And then we're getting a bit longer. Then it start to check. Yeah, it turn into fracture torsional buckling. Okay, of the beam in here. Okay.
So it seems to be partial buckling, but there is no shift.
No flexion is complete.
What do you mean?
It looks like a partial buckling.
It look like that. It does a little bit. We don't see that, but it has a little bit of the shift over. It means that it's probably, you know, the equation maybe FOZ control a lot of them, but FOX very small. But when we increasing that, you can see it start to get, all right? Now, what I really I'm interested to show you is when you get longer, oh, not yet. Okay, so what happened is with that section we can't see that, but I will be very interested to show you what I mean later now. So I changed the flange a little bit smaller, and I show you what I mean now in what we learned, okay? So let me just get back to that. And then we change the dimension, section. So let's say here, section. And then we can dimension. So in here, what I want is maybe not 75, but I want 40 maybe. All right, so something like that. So the reason I want to show you is I want to show you the column where IX is a lot smaller than IY. So what's happened with when you design it as is compression. So when you run section analysis, okay, you got property, but when you run analysis for uniform loading, you got, okay. All right, so this is the signature curve, right? So you can see the distortional buckling going up very, very high. So it with that section, it doesn't open easily, but it's, yep. So the distortional buckling strength is good. Now what I'm interested is here, right.
Is it because of steeper flange?
Yes, steeper flange, and you can see a decent size of the lip. That's why it gives a lot stronger or stiffer distortional buckling. So it gives you a pushing that halfway, that local, distortional minimum point up. All right, so that's what I want.
It's purely flexible.
Yeah, that's what I want to show you. Look in the equation. Look back into your lecture note. Page, yep. So page 23. You got page 23 here? So 23, where you got FO, FOY and FOZ. FOXOZ, right?
It's a FOA.
Yeah, you see that there's two options, right? And we choose the lesser one. You remember? So then in those equations you have is, yeah, it depends on length L. Okay? Yes. So when L is very small, then it means that when you got short column, for example, you design for 2 meter, maybe. So you can see that is buckle sideways and twist. So that is the equation FOZ will come in. It will be smaller. Yes? All right. Now, if you increase the length to 8,000 or something, and it's just buckle in flexural, pure flexural buckling. So that's why the equation FOY will come in. So that is why we choose the smaller one. So exactly what's going on, showing you different failure mode, right? It's same Euler equation, but it's changing the mode. Right? How interesting is that? So you can learn a behavior, and the number tell you something, not just you have to plug in, choose a smaller. Why we have to choose smaller? That is happening in here. All right. So in this case, how you gonna do it? You have to put the knocking to reduce the L, and then make it better. Right. So that's how it works. Good. Everyone clear? Now with the localized loading, you don't do it in this course, but you can do it right now. Is you can apply the, I can unlock it. So in the practice, you might have some cases like localized loading, and you got the boundary condition. So let's say you got a beam simply supported at the two end, and you apply one load in the middle. Okay. And then that's how we're gonna do. So then this is simply support at the end. Now I want to apply the load at one end. So we apply the localized loading. And then here telling you where you wanna do it, what case. So in here we wanna do it this case. We put one load in the middle, and we wanna, now the lengths come in. And they will ask you what length you want. So I want a beam for like 4 meter. And N is the bearing length. So I want probably 200 millimeter that acting. So like, yeah. So in the practice, like you have the purlin sitting on the flange, top flange of a girder. So it's pushing down.
Stiff bearing length.
Yeah, this is the bearing length of the load. So like 200 maybe, yeah. And this is showing you where you're gonna put it. I wanna do it right in the center, the 0.5. And this is the load. So I want to put the load downward, so like 1,000, upward or something. Let's say apply a little bit long, so maybe just we just do a smaller length, and it is maybe just 50. That's easy for you to look at. Apply. Okay. That is how we can see that. Oh, so this is pushing this way, so Fx. So I want to Fy this way, so we can change it. Assign localized loading. And this one you change into 0, and you can choose Fy, but put minus, it's going to go down. Okay, that's it. And then you, another one, you're going to go to here, and then you can choose the boundary condition. That is what we did. We're gonna choose the series term. So remember, I'm talking about last lecture, right? In order to pick it up, you need a lot of term to pick the localized loading. So in here, we need 50 term to get it. So then we run it, and we see what's going on. So we choose now, in this case, you choose that one. You see there's two analysis we need. First is you run pre-buckling analysis to get a stress distribution. And when later on, once we've done it, and then we will fit the new stress distribution into the buckling analysis, and we run it. Yep, you can see how long it is, because you make a 15 term, and then think about the metric. You got a 1 term is that, and you got a 15 is how big is the metric that need to be solved. So it's going to expand that a bit for computer analysis, but that's fine. That's how the computer running, and then give you. Right, and then you can see here, if you click on here, you see that we're pushing down, okay? I can turn around. That when you're pushing down and you got a local buckle, you got all the web rippling like this one. This is the and this is because it's localized loading. We don't have signature curve. We don't have every single halfway. What we do, we just focus on the length and the failure. So here is give you some stress distribution. As you can see, we got a because it's pushing down in the middle. Of course, it have the normal stress. It looks like a beam because it's bent. But then you got a transfer load in here. That is shear load. You see how it's pushing down. Okay. But now, if you really want to keep it, you have to put the restraint to keep it. Let me have a look on the barricadation where you in the practice you can hold that, right? So you put the restraint here. And you can put like in 15, right? Like let's say I want to put on the node 15 here, I want to put that restraint about X. I click on here. So I want to, like you got a road, the bar, right? So you hold that one and you see how it works. Apply, okay, run it. Then you analysis, you run that. And you can see how it works. Okay, it's done. Good. So you can see if I click here, it's still there. Okay, you can see that. Now that line is straight, right? But the bottom plans, from how you press it, is buckle out. So I'm gonna stop the bottom plans as well. You can see the pure localized loading. Okay. So we unlock it and we put another restraint on that. So what else I want is 27, isn't it? Okay. Let's have 27. And I want to stop that one from here. Apply. Okay, and then run it. So it gives you a lot of flexibility. Whatever you want, you can run it and then try to understand the behavior, importantly. And Wi-Fi is very interesting. You can try the very fundamental all column problem. You draw, you create and run it and see how you can compare with yes, very fundamental all column equation. Right, so you can see now it's sort of localized loading. This is pre-buckling, that's it buckling. Okay, you can see that if you're pushing one end, at the end it's localized in here, right here. You can see that a lot of localized in here. So that allows you to do analysis on that based on finite strip method, and you can pushing down. Right. So you might ask me what we need to do with this one, and then what is this part of the direct strength method for localized loading we're developing now. So this is part of the pre-critical that you need. And then another one, we have to develop the direct strength equation. And the other very important job that we need to do is PY, how to work it out, the U moment, U model, plastic mechanism model for localized loading. And once we finish that one, you're gonna have a beautiful, nice direct strength equation for web crippling or for those types. So you got THIN-WALL, you run that, and then you got a model that we're developing now for PY, put all together in one equation for DSM, and then you got the load that you want. So it's in future. We're developing now. I promise you, once we have that, we will share with you, okay? So other than that, you can go here, and then we can go to DSM localized loading, but not available at the moment, okay? So it's all here. Right, you can go to here, you can see web crippling. You can see that this is the shear, a little bit funny there, but this is the transverse stress. When you put down, you can see the transverse. And because this one you put in the middle, you got a normal stress as well. So all the stress distribution you have. And then that is what we want to do it for you today. And the report in here, you can export report. You can choose whatever you like. And a good thing in here is with the 3D model, and you got that, okay. This is really web crippling. Okay, so this is really web crippling, okay? So it's actually buckling, that one, okay? You can see it's very localized. So the beauty of that is you can export picture. So you actually can export that into the JPEG file or in any picture format, and then you can put in your report, okay? And turn around, and you show it different colors, everything. All right, and then you can put save as here, and you can save into any format that you want, JPEG, you name it, okay? I think that's it. That's anything that I want to share with you. Of course, there's a lot of things you can play with that within that program, but in general, it's just showing you a bit of snapshot about what can be done, and then that's good. Now, any question?
So in case of a 4-1 bending, can we put two loads for the same thing?
We haven't developed yet up to that. At the moment we have only one load in the middle, but you can move the load, but just only one load at the moment. And of course we have two cases. One is one flange, and the other maybe we put another one, so it's two flange loading. So we deal with the localized loading. We don't deal with the bending. 4-point bending is more. So then with that one, you come back to the uniform loading, uniform cases. Yeah. Yes.
Can we include the service walls? Service walls in this element?
You include opening, a closed section. Oh, we do. You can do it. You can do it closed, but you have to. Opening. Okay, so at the moment we haven't got that one in the program yet. Later on, we start to think about, but very tricky because it's finite strip. So that everything you do is strip. So you can't have discontinuity in the middle. Okay, so that's why we do a little bit of fudging around by, if you have multiple holes, we replace by one strip with different thickness. what we call is the equivalent. Yeah. So that is the way that we can do with finite strip. But in general, because finite strip is a continuous strip, so we can't do it. Yeah. We can do it with spline finite strip, because spline you need to deal with every segment, the length of the member, and every segment is the one spline. So you can cut in the middle, and you can model it. So I had a couple of papers modeling the THIN-WALL structure section in shear width holes, but I'm using spline finite strip. Yeah, we can't use this one because it's going to. Yeah. So the way we do, and I think we fake a little bit, is we put the strip along, but we put the thickness is 0. So that's where we got the TG. So in that we put TG is 0, but T bending is the actual thickness, but TG we put 0. So that's why we can work around that problem. Good question. Yeah. Yes. So I hope that you have a bit of time later on. Yes.
Here the application of this local load in the centroid of across the section.
The loading.
Yeah, loading.
The loading here you can.
Loading, application of the loading.
Yes. So this one is actually, that's good. So you can see here the load you can choose anywhere. So the load here at the moment. So at the moment you see here the loading point. The loading point is what is that? The node number 11. So node number 11 is around here. Okay, so you can click on whatever node you want. You can put in flange or lip or whatever. You can move the load. Okay, you can put load anywhere. So in the practice, maybe you put a load where you put a screw up. Exactly, it's the middle of the flange, for example. You can do it. Yeah, anywhere. Okay. Okay, I forgot to show you how to input the from Excel, right? So we actually, I create a section here. I put in Excel here. I create an I section. So what I do, I just highlight that and I copy, and then I go up here. And then I go up here again, and then I want to create another section, and I click on General, and I put here, and I can paste. You get? Yeah, you can paste that, and then you apply. Okay, so no. All right. Not this one, not that one I like. The section. That is the general section I like. All right, so that's the problem now, because the strip is not like what we want, right? So then you can always change that. You go to section, and now you go to section data. Okay, so you remember now what we need to change is so we need to change that element, right? And to make sure that it's quite good. So what element is missing here? It's too hard to see. Okay, so like 17, let me see. 718. 718. Okay, so like 12, 17, yeah? And then what is that? 17 to 18, right? So what we want is we want some element here from 20 to so from 5 to 20, from 5 to 20, 21, right? We want that element 5 to 21. 5 to 21 and see what's happened. See, we can fix that one. Okay. Now is this one is I want from what is that 30? Can't see that clearly. 22, right? 22 to 21. So we want 22 to 13. So this one is 13. No. So we want 13. See? Right, so now you got that one. So you can play around with that. Actually, you can connect whatever you want. And now you can increase the the top flange. For example, 1, 2, 3, 4, 5. You change into element bigger. Number 2, maybe. Number 2. 4. Yep, apply. See, so you're gonna have the flange bigger. Right, so that, with that, any question on that? So hopefully then thank you. I will see you around. Thank you.